Yeah, Rajkiran. Can you see the slides?
Yes, sir.
Yeah, so start.
Okay, sir. Please send it, set in presentation mode, sir, please.
Yeah. Yes, please.
Okay, good evening, everyone. Today's topic is cost optimizing heat treatment. So, the fuel cost is the major contributor in heat treatment shop. So, it's the major cost contributor are fuel, heat losses, quenching media, process selection, furnace atmosphere, fixture and loading pattern, and geography. So, let us see one by one how they are contributed in heat treatment processes. So, first is the fuel. So, we have compared the four types of fuel, that is PNG, LPG, electricity, and propane. So we are categorized in four types, that is the calorific value, gigajoule per ton, cost per unit, and cost per ton. If you see the gigajoule per ton, the PNG required a very high gigajoule per ton. Sir, again slide is on display. Hello?
Yeah, can you see this?
No, sir.
Can you see the slide now?
No, sir.
माई इशू वो आपका को होस्ट हट गया था, अभी दोबारा करिए सर, डू इट अगेन.
Okay. Yeah, can you?
Yes.
Can you?
Yes, sir. Can I see that? Okay, so come to the point. Again, we compare the graphs of the gigajoule per ton. So in case of PNG, it is the higher gigajoule per ton required as compared to other fuel. But in case of the cost, PNG cost is very less as compared to other fuel. So that the PNG fuel is economical. Sorry. So PNG fuel is very economical as compared to the other fuels. Next, sir. So before going to cost optimization of any furnaces, we should know our furnace efficiency. So by this formula, that is heat output divided by heat input into 100, that is the heat in the stock in kilocalorie divided by heat in fuel or electricity in kilocalorie into 100. So we can calculate the furnace efficiency. Also, we should know our specific energy consumption, that is the quantity of fuel or energy consumed divided by quantity of material process. So by calculating this specific energy consumption, we can set the target, what is the current consumption, and then we can set the target, how can we reduce the fuel consumption. So next. So by the scientific formula, thermal efficiency can be calculated by Q is equal to M into Cp in bracket T2 minus T1, where Q is the quantity of heat is required to heat the material from normal temperature to carbon temperature. M is the weight of the material in kg. Cp is the mean specific heat in kilocalorie, kg degree Celsius. Normally carbon material, the specific heat is 0.44 to 0.49. And T2 is the final temperature desired. And T1 is the initial temperature of the charge before it entering the furnace. So next. So before that, you should know the various types of heat losses came out from your furnaces. That is, are the heat loss through the exhaust gases, either as a sensible heat, latent heat, or incomplete combustion. Heat loss through the furnace wall or heat loss to the surrounding by the radiation and convection from the outer surface of the wall, and the heat loss through the gases leakage through cracks, opening, and doors. So we have to identify the various possible causes from the furnace where the heat loss can be taken place. So next. So that possible causes we have to put in Ishikawa diagram, and that is put in the five parameters, that is equipment, recovery, waste heat, combustion control, insulator, and operation. And we have to validate that possible causes where we can eliminate the heat losses, so that on the basis we validate that possible causes. Next. So you should know how to calculate heat losses from your furnace by some scientific formula. The Bureau of Energy Efficiency given us some formulas to calculate the heat loss from the outer surface of the furnace. So there is one method is convection heat loss from the surface of the furnace. the quantity of heat loss from surface of furnace body is sum of the natural convection heat loss and thermal radiation heat loss. So we have to capture the numbers of temperature of the outer surface and take the average of that surface and put this temperature in this formula. After that, there is given that is Q is the quantity of heat release in kilocalorie per watt per meter square. A is the factor of the surface of natural convection. If his ceiling is 2.8, side wall is 2.2, and earth is 1.5. And T1 is the temperature of external wall surface, and T2 is the temperature of air surrounded to the furnace. And E is the emissivity of the external wall surface of the furnace, and that is around 0.4 to 0.5. So when you put this all the data in this formula, we get the heat loss in kilocalorie. And again, that kilocalorie energy, we have to divide it by the calorific value of the fuel that we are using, maybe PNG, LPG, or electricity. Then we will get the actual amount of heat loss in terms of units. Next. The second method is to radiation heat loss from the surface. We already calculate the average heat loss from the surface. In graph, you can see that in x-axis there is the temperature, and y-axis is the heat loss in kilocalorie. So you plot this graph by the temperature, and in the right side we get the kilocalorie heat loss. Again, that heat loss, it may be ceiling, side wall, or maybe earth. Then combine this all three losses and again divide by calorific value. So we will get the heat loss in terms of units. So next. So this is the one example how you reduce the heat loss by thermoceramic coating. When we heat the starter furnace, initially at the lower temperature, our refractory emissivity is higher, is around 0.7 to 0.8. But after increase in temperature for above 600 degrees Celsius, our emissivity of the refractory is going down nearby 0.4 to 0.3. So that our addition is passed through from internal refractory to outer surface, and the outer surface temperature increases. And as we know that the higher the temperature pass to the lower temperature in ambient temperature, so heat loss is taking place. So that this thermoceramic coating is applied from internal surface as well as external surface, so that your internal refractory's emissivity has been increased from 0.3 to 0.8, and that radiation initially was passed by external surface, again pass inside the furnace, and the heat loss is been controlled. Similarly, we can see in the image, the before temperature of the furnace cell is 109 degrees Celsius. After coating, it is 92 degrees Celsius. So around 60 to 70 degrees Celsius temperature is reduced. So that amount of heat can be saved because of the external surface temperature drop down. So in that, because of that, we can save around 40,000 of SCM, and annual cost saving around 17 lakhs. The life of that coating is about 3 to 4 years. After 4 years, initially by year it is deteriorated, cost saving deteriorated because that coating is deteriorated. So initially we get the 10% of saving, but after some year later is decreased to 5%. So after 3 to 4 years, we again coat that thermoceramic coating of the internal surface, and again we get the same results. So next, this is another example to save the cost of fuel. From furnace exhaust, we can again recover the heat, and that heat we can use in the another process, just like the charge preheating or the heating of the pre-washing or preheating bath. And again, we can pass that hot air to the burner, so we can increase your burner efficiency by 30%. So that's method we can save your cost also and fuel also. So next. This is one of the table given by Bureau of Energy Efficiency, where we can identify the various heat consumption in terms of charge heat input, sensible heat loss, moisture content heat loss, or CO losses, as well as the cooling water losses. So with the help of this table, we can calculate the furnace efficiency as well as the losses of the furnaces. So next. Another table given by the Bureau of Energy Efficiency, where heat loss in flue gases based on excess air can be given. If your burners given a specific air ratio from fuel to air, that is based on your fuel, also PNG, LPG, or whatever may be, so that on this standard ratio, you have to maintain to optimize your consumption. If you increase the air ratio by 25, then your fuel exhaust or fuel wastage increased by 48%. If you increase 100%, then your fuel exhaust increased by 70%. So that your burner ratio should be maintained properly for optimization of the burner efficiency. Sir, next. This is another table given by the Bureau of Energy Efficiency. This is the thermal efficiency for common industrial furnaces. Here, low temperature furnaces, high temperature furnaces, continuous kiln type furnace, and ovens. Higher temperature, higher the heat loss, and lower the inside temperature, lower the heat loss. Because higher temperature, again heat will pass from the internal surface to outer surface and again pass to the atmosphere. So that our outer surface should be maintained between 40 to 50 degrees Celsius. So there will be your fuel consumption can be controlled. So next, come to the quenching media. So there are 4 types of quenching media nowadays we can use for the quenching of the component. That is oil, polymer, gases, and salt solution. Normally, oil consumption per ton is 1,200 rupees, and as compared to polymer, it is 300 rupees per ton. Gas consumption is around 30 to 100 per ton, and salt solution is 20 to 100 per ton. There are 4 types of oils are available for quenching. That is medium speed quenching oil, medium fast speed quenching oil, fast speed quenching oils, and mark quenching oils. And in right side we have given table, that is the viscosity range, flash point of that oil, and the normal operating temperature of that oil. So while doing any component processes, we also select the proper quenching media for that component. Suppose your requirement of the quenching oil is around 120 degrees Celsius, and suppose we have used the operating temperature oil is the 80 degrees Celsius, then your oil property is deteriorated because we have increased the oil temperature beyond the normal operating temperature. That case, your oil property deteriorated, and that will impact your final product material quality. Maybe your component quality is not get properly. Maybe that effect on your ECT, surface hardness, pore hardness, as well as the microstructure, and also that will increase your cost of poor quality, maybe rework, rejection. So we have to select your quenching oil precisely while doing any process. Similarly, polymer quenching, 2 types of polymer quenches available, that is inverse solubility and is up concentration type. In inverse solubility, this is the special property available in polymer. When we quenching any component in polymer, after that bath temperature increase beyond the 70 degrees Celsius, that polymer is again separated from water and create the one coating or one a protective coating along the component to avoid the direct cooling rate of the water. And that gives the proper cooling rate of the component transfer to the Martin side. And again, that bath temperature down below 60 degrees Celsius, again that's polymer mixed with the water. And second is the up concentration type polymer, that is the similar to the oil quenching polymer. Here we can set the concentration from 5% to 20 or more than that, and on that basis we can set your cooling rate that we require for the quenching of the component. So in table we can say that we have given the viscosity of the polymer and normal operating temperature of the polymer. In case of polymer bath cost consumption, there should be some limitation also to use in polymer in furnaces. In batch furnace or continuous furnace, you cannot use the polymer because of the mix of the water or water vapor issue. But here is the open oil quenching is available, or induction heating, we can use the polymer. Also, polymer bath health regarding, you have to agitate that polymer in every 24 hours. Otherwise, the bacteria will be formed in that polymer, and also the property of the polymer deteriorated. That will impact your final property of the component. That will be rejected or reworked. And also, after deterioration of the polymer, that will be scrapped, and that cost of that polymer, it will be increases. Third thing is the gas quenching that will be used in the vacuum. That is nitrogen and helium. The cost of the both is higher, but we can again regenerate or reuse, recapture or reuse that nitrogen, collect that nitrogen, and again reuse for the quenching. So that can be reduce the cost of that gases also. Then fourth is the salt solution. It's 2 types of salt solution available. That is mark quenching salt or hardening types of salt. But there are some limitations or some losses or some obstacle for this salt solution. There may be high energy required for maintaining the temperature of that bath. Also, there of the wastage of the salt with the component, and the soil pollution also happen because of the salt solution. And that is used for the mark quenching operation or quenching of high steel, switch steel, or tempering or hardening process. And before this, selecting the any quenching media, they are keep in mind the distortion. A distortion is a major contributor for the post-processing operation that require the grinding stock, grinding operation, as well as if you use the oil quenching, they require the short blasting, short pinning, and setting operation. So that additional cost will be increased in the product quality, product cost. Sir, next. I already told we have to maintain your quenching oil property to get the precise result of your component. So we have to check your quenching property every 3 months by giving the sample to the checking the sample of the quenching oil. That is various property we have checked, that is viscosity, cooling rate, acidic values, saponification. All these properties should be checked every quarterly. That should be plotted in the graph. That is easy for to compare the month-wise comparison of the any property of the cooling rate, and you can immediately take the action. That can be add the additives, or that can be add the low viscosity of oil. Even though we can analyze that that is the filtration. We can schedule the filtration of the oil on this basis of this graph. So next. This is one of the example where we have changed quenching oil with the polymer. We have one type of open oil quenching furnace here. So we have decided to replace this quenching oil with the polymer, and that I already told that is up concentration polymer. So we have take the trial of this polymer with the component and set the proper concentration with increasing the that polymer inside the water, and get the desired result of the component and set and replace quenching oil with the polymer. So we have eliminated the heaters from the quenching oil that require for the maintain the oil temperature up to 80 degrees Celsius to 100 degrees Celsius. And here in a polymer, there is no requirement of heater. Also, we have eliminated the fire hazard from the premises, and because of that, the operators feel safe to operate in that area also. So this is one of the good example. We have reduced the cost of the quenching media, as well as the unsafe condition has been eliminated. Here we save around 10 lakhs per annum cost from this replacement of oil with the polymer. So next. Next.
Just a moment, I'm not able to do that.
Okay. Okay.
Yeah.
Okay. While deciding any component cycle, we have keep mind that the cycle. So previous slide.
This is the next slide. Yeah. Process selection.
No, sir, before that, carbon concentration. Okay, sir. Next slide, sir. Next slide. Okay. Process. Sir, process selection.
Yeah.
Okay. Come to the process selection.
Yeah.
Okay. So we have deciding the any process, carbonizing process for any component. We have to consider that which type of final product quality requirement, what is the material grade of that component, and what is the cost, minimum cost required for the component for the processing. So there is the three types. We have considered here three types of the process: that is vacuum carburizing, convection heat treatment, and the induction hardening process. Vacuum carburizing is an advanced process for carburizing, carbureting process. Here, consider the various parameter. That is, the cost of poor quality is negligible in a vacuum furnace because of the absence of the oxygen. So there is no possibility of the intergranular oxidation as well as the surface oxidation. Here we get the uniform case depth, uniform core hardness, as well as the precise microstructure. So cost of poor quality because of the rejection and rework is negligible in vacuum furnace. Distortion control is very good here. You get maximum 30 to 50 microns distortion in this component. Also, inventory carrying cost is very low because the short lead time. The cycle is very short in vacuum furnace, so that the inventory carrying cost is very less, but maintenance cost is very high as compared to other furnace in vacuum furnace. But it is compensated because of the productivity as well as the inventory carrying cost and post processing cost, and the poor cost of poor quality is negligible. Also, because of this, OEM can give the maximum warranty of the component because of the quality of the vacuum furnace. So that all things is compensated with the maintenance cost. Then the capital cost is high in vacuum furnace. So we consider the conventional heat treatment, the cost of poor quality is high because of the presence of the oxygen in the atmosphere. So that the grinding process is required for the remove that oxide layer from the component, so that the excess grinding stock to be maintained on the component, so the cost of the metal is increases. Also, post-processing cost is high, that is the short pinning, short blasting, as well as straightening operation. And the lead time is 24 hours, more than the 24 hours. So the high inventory should be maintained. The inventory cost also increases in conventional process. Maintenance cost is low as compared to vacuum furnace, and capital cost is moderately high. And come to the induction hardening process. Here we can use the thin part, or where the through hardening part is required for the hardening. So we are use the induction hardening process where there is atmosphere is not required. Cost of poor quality is low in induction hardening process. Mass production, cycle time is very short. As well as we can set the single flow by carburizing, carbonitrading. Also the tempering, we can set the single flow. Electricity consumption is high in induction furnace, and precise control possible in heat treatment, and beneficial for smaller part, and capital cost is very low in induction furnace. So we have to select the proper process for your component. Also maintain the
खरी हो जाएगी।
Hello, that is my issue.
भले भले, अच्छा।
Yeah.
okay, sir.
So it's my issue. Can you see the presentation now?
No, sir.
No.
कांदे दो ना।
अनु कौन है? Yeah, Sandeep, please share.
Yes, it's visible, sir.
Yeah, good.
Yes, it is visible.
So next slide. Yes, sir.
You're good.
So while deciding any carburizing cycle for the component on the basis of the requirement of case depth, so we have keep in mind the their process selection as well as the carbon potential, temperature, and cycle. So here I have explained the two types of cycle is single stage cycle and boost cycle. In single stage cycle, carbonyl is one constant carbon potential throughout the carbonyl cycle and result in the carbon concentration gradient with the concave curvature. We can see that in the second graph, the curvature of that KZF is convex. Because of that, when you do the grinding of that component, there is the surface, the KZF is decreases, so that the wearization property of that component has been decreases. So that in second boost cycle, boost carbonyl uses a high carbon potential for most of the cycle time. But at the end of the cycle, the carbon potential is lower to meet the hardness requirement. The resulting carbon concentration curve close to the surface is convex. You can see it in image, the curvature is convex. The 0.8 KSDF is around nearby 0.2 mm. So that if you 0.2 mm, so you can grinding around 100 micron, 150 micron. There will be also a 0.8 KSDF is available. So that because of that, the grinding allowances is available and high wearization property is achieved because of this boost cycle. And because of that also the carbonyl time has been minimized. So next.
Just a moment, it's taking time.
Yes. Here is the one good example, comparison between single stage process and two stage process. A is the equal carbonyl time and B is the equal carbonyl depth. In A is the identical total carbonyl time is 5 hours fixed. And there is increase in the depth from 0.87 to 1.1 mm. If you consider single stage, you can get the in 5 hours is 0.87 mm case depth. But in the same time, in two stage, you get a 1.1 mm of depth, increasing the 0.26% case depth. In second graph, the case depth is fixed, that is 0.7 mm. So on that basis, we have set the cycle time. So single stage cycle, we require the 206 minutes for the 0.1 case depth, and in double two stage, we can require the 146 minutes for the 0.7 mm case depth. So we have decreased the cycle time by 29%. So that if considering the high productivity is prepared, then the boost carbonyl cycle should be used. So we have used this boost cycle to get the optimum result and the optimum utilization of the fuel. So next. This is one of the example where I can reduce the cycle time. We have analysis the cycle by element wise, that is enrichment cycle, diffusion cycle, hardening cycle, as well as the top cooling cycle. This is the ring gear cycle where we have hardened the carburized the ring gear in one furnace, again unloaded, cool and unloaded, and again rehardened in another furnace for the press quench. So we have identified here the hardening process is repeated in carbonyl cycle also, in another furnace also. So we have eliminated the hard cycle here, that is around 60 minutes to 5 minutes, and the top cool where you maintain around 90 minutes, we have reduced to 55 minutes. So here initial cycle is 12 hours, now reduced to 12.5 hours. So we have reduced here cycle by affecting the final property of a product. So we can save around 10 lakhs per annum here. Also lead time reduced by 12%. So this is one of the good example for cycle time reduction by avoiding impact of any product quality. So next, come to the furnace atmosphere content. Here we have used the 4 types of atmosphere, that is indoor gas, nitrogen plus methanol, LPG plus CO2, that is the fine carbonic atmosphere that mostly used in the high temp furnace, and vacuum atmosphere. Considering the endothermic gas reaction, that is CO factor is 18 to 20%. So that the possibility of the soot formation as well as the IGO and NNTP is higher possibility in the endogas. And if the system that is more than the endogas thermic reaction, so that is the possibility that IGO and NNTP is more. But considering the cost, the endothermic gas required around rupees 5,000 per ton, and in consider nitrogen methanol is 900 rupees per ton. But in nitrogen methanol system, we required the storage capacity of the methanol system that required some legal compliances also, and the storage cost also more, and the maintenance cost for nozzle and all these things also more. So, and quality point of view, the endothermic gas reaction is the more pressure given in the atmosphere, so that the final product quality and cost of poor quality is lower in endothermic gas process as compared to nitrogen and methanol. Considering the fine carbonizing process, there is a limitation of the shallow case depth. This process is only used for the shallow case depth. If you want, that is nearby 0.5 to 0.7 maximum. If you want to increase the case depth in same process more than 0.8 to 1.9 mm, the cycle time is required double, so that the cost, so that the fuel or the energy required is double in the process, so that the cost is increases. So average cost required for this process around 200 per ton. In vacuum furnace, there is no CO factor, so that there is no formation of the soot, and the cost required per ton is 3,500 rupees. So that most of the companies use the endothermic gas reaction for the reliability and constant quality. So next, come to the fixture and loading pattern. This is one of the major contributor in the process of the heat treatment process of the component. On the basis of the requirement of the component or production, if you use the mass production, then go to the of real. If you do the batch type or single part heat treatment, then you go to the low cost fixture. Because in mass production, if you have selected the high grade fixture, then that gives the maximum life, and that cost can be accumulated by the productivity. There are some HU, HX, and Mansell type of grades are available that can give the maximum life, and in table that give the grades or composition of that base rate, that is HU. If you consider, there is the 17 to 20% chromium and 37 to 14% nickel. And in HX, that is in 15 to 19% chromium and 64 to 68% nickel. So that because of the nickel and chromium, the base tray can sustain the higher temperature. And at that higher temperature, because of the nickel, base tray can increase the stiffness. The base tray strength and stiffness can increase because of the nickel. So that you get the maximum life of that fixture. Also, considering the loading pattern, you can utilize the maximum capacity of the furnace. And that means consider the maximum furnace capacity. It may be 1,000 kg or 1.5 tons. So we have decided the 70 to 30% ratio in between that. Means that we have to load 700 kg of parts and 300 kg of the fixture. So we get the maximum capacity utilization of that furnace. So next. One more thing, HU, HX, and Mansell grade having a SCP type of macrostructure. So that structure cannot be pick up the carbon, so that the distortion as well as the hardness or brittleness is not increases of that tray, and that gives the maximum life. This is one other good example of the capacity utilization. In first image, before condition, we can see that we have load only the single loading pattern in the tray. So we will maximum utilize the 76% of that capacity of the base capacity of the tray. In second term, so we have changed the loading pattern with the fixtures, and we have loaded the 37 number of pinion in that tray. So we have increased the capacity nearby 99%. So your tonnage increased by 27% and a capacity increased by 405 part per day. So next. This is the schematic view of that improvement. This is the before condition. We have loaded the component in single layer, and this is the after modified loading pattern. We have loaded the double loading pattern by avoiding the shadow effect of the component. The component load by one another, so we have capacity utilize maximum here. This is another example. Here we have loaded the 2 layers of the gears, but after we have found that there is some space where we can load excess material. So we have down the lower rod below and up the upper side, and put the excess rod in between of both. So we have increased that capacity of the furnace and utilized the complete capacity. And this is the before condition, only 2 layer loaded, and it's another it's after condition, we have loaded 3 layers. So before it utilized only 68%, after that we have utilized 100%. So next. This is the fixture reconditioning. After continuous using heating and cooling, our fixture getting bent because of the continuous load. Also the length has been increases because of the thermal expansion. So that we have sent this part to our vendor. The vendor is again heated the part and straightened, and again excess part has been cut and again welded by Inconel, and again we use that part for next 6 to 8 years. So by this way we have reduced our fixture cost. So next. This is the other part example. This is a before condition, and after reconditioning, the part are straightened, and again we use for next 6 to 8 months. Then come to the geography. While considering set up the new plant, heat treatment plant, so we have considered the following point, that is the electricity traffic in that tariff in that area. Maybe rural area, urban area, industrial area. That the tariff is different in that area. So we have decided on that basis. The logistic cost, we have set the plant nearby the supplier or customer plant, or the availability of the raw material to be considered. Otherwise, logistic cost is very high, and that could be included in the process cost. Also, labor availability and the labor cost is the most important. If you consider the Mumbai or Pune region area, the labor cost is very high. But if you go to the outside this metro city or the in rural area, the labor cost is very low. So that will be impact in your final product cost. So this all the ideas and all the events are explained, and now presentation is over here. Thank you.
Yeah, thank you very much, Raj Kiran. We have taken a lot of efforts and into taking consideration of all the factors here. So let me see if there are any questions in the chat box.
Sandeep, I'll take 2 minutes.
Yeah, sure. I'm sorry, I didn't see you join anyway. Yeah. So let me introduce our chairman of India chapter, ASM International India chapter, Mr. Sudhakarji Bonde. He would like to say a few words about the activities of India chapter. So over to Sudhakarji. Yeah, Sudhakarji.
Am I audible?
Yeah, sure. Yes.
I hope Mr. Rajkiran must have given you tips to reduce the cost. Jayesh Mukadam must be very happy.
Yes.
Huh?
Yeah.
Yes.
So, myself Sudhakar Bonde. I got late, so I want to tell you regarding our ASM International India chapter and appeal to people who are not yet member of this our chapter. They can take benefit of our membership, and the membership details are available, means application forms and what we are doing and what we can do and how you can get benefited. That you can see on www.asm-india.com. So please go through our website, and if you feel it is interesting and you can get benefited, so please do join us. And in case of any difficulty, you can contact our office, Dr. Vivek Singhal. He'll be able to help you out on this. Now about the ASM International in brief 1 minute. ASM International is a society formed in USA and it is headquartered in Cleveland, Ohio. We are based in Mumbai and now we'll be operating within a month or two from the Bhandup office, and we have the precious premises acquired there, which is having all library, conference room, and all the things needs which you can utilize for your benefit. So I humbly request you to do the consider the joining of this, particularly Mr. Data. I thought he's there. I think he has not yet become member of ours. Anyway, now I have some pleasant tasks to do now. Today we are celebrating the birthday of our secretary, Mr. Sandeep Rege. So let us say happy birthday to him, and he will be sending the cake to everybody. Mr. Sandeep, happy
Thank you
birthday
very
to
much.
you.
Happy birthday.
Thank you.
Happy birthday, Sandeep.
Thank you. Thank you.
Ah.
Thank you all. Yeah.
So this is the occasion. So this lecture was kept for his birthday.
Happy birthday,
celebration.
Sandeep.
Thank you. Thank you. Thank you, Bhatshan.
So I think you will not repent becoming the ASM member. You can try it for 1 year, and if you are not happy, you can very well leave. So I'll again appeal to become our member so that we can have the knowledge sharing both ways. And that is basically the aim of the ASM International, to have the knowledge sharing base, have the contacts, have the complete literature which is reviewed by the peers, and we have the material handbook. We have the very well equipped library. You can take benefit of that. That is not chargeable. That is free of charge to all members, and you can even receive the journals and other things and details. And basically, we will have interaction with the people who are directly in the business. Okay, thank you. Thank you very much for the patient day.
So I
Sandeep.
think there are a few questions. I'll take them. Yeah, Mr. Santosh Taparji, he's talking about our recovery method suggested by you for nitrogen in vacuum furnace as well as heat recovery through exhaust flue gases are practical in terms of economy. Yes, if you are nitrogen in vacuum furnaces, when you are quenching, there is a quenching that recovery is around 65 to 70%. Of course, when you are in with nitrogen, the volumes are very high. Then I think you can utilize that recovery method, this thing method. And if it is helium, it is still definitely economical. Of course, and the heat recovery through exhaust flue gases are practical in terms of economy. Yeah, one more point in nitrogen and helium, the cost of transportation is going day by day up, and the cost of nitrogen also that we're going day by day up. As you are aware that since we are running vacuum furnaces, we started off with 4k rupees a kg of nitrogen. Now it's almost more than double. So that happens. That is one of the impact of nitrogen cost, and that can be definitely, with the heat recovery system, it can be definitely worked out and could be economical. About the exhaust flue gases are practical in terms of economy. Exhaust flue gases, yes, because that exhaust flue gases we ourselves are using in Mahindra for many other aspects, and majorly we are using it for our heating of our post and pre-treatment baths. And of course that is that can be utilized for this. Even sometimes that can be utilized for even oil quenching, I mean heating of the oil, by doing the proper manifolds properly utilized. That exhaust flue gases I've seen being used by many other people. Can you explain how we can reduce the refractory losses? Yeah, of course, that refractory losses, I think BRP, I don't know who's this Mr. BRP. If you can identify yourself, that would be better. But definitely we can reduce the heat refractory losses, and that can be utilized, that can be done by many coatings which he explained recently in this thing. Can you explain single stage and boost carburizing process and the cost benefit by changing the process? I think Rajkiran, can you take this question?
Yes, sir.
Yeah.
Sir, already I have explained in the graph. In case of single stage, the cycle, we have maintained the CP uniform throughout the cycle. That is nearby 0.8 or 0.9%. And the temperature also constant. So that condition, the carbon pickup or boosting of the carbon in the throughout the in the component nearby the case depth is very slow. After that, the cycle required is very high. Also, the profile of the case depth is concave, so that the grinding possibility of grinding stock is very less. So that will impact over the quality. And in case of boost cycle, we have maintained the higher CP nearby 1 to 1.1 mm at the higher temperature. That time, maximum CP carbon is deposited towards the core or towards the case depth, so that we get the maximum case depth in short period of time. And we have reduced in hardening stage the CP nearby 0.7 or 0.8 that is required. So your surface hardness is maintained as per your requirement nearby 60 to 61 to 62 HRC, and the possibility of RA or any carbide has been negligible in that condition, so that the boost cycle is very economical for this any mass production.
Yeah. There is another question. Explain the point of nitrogen plus methanol feed versus LPG plus methanol feed. LPG plus methanol comparative benefits. LPG plus methanol.
Yes.
Mr. Mandral, yeah. So not heard of LPG plus methanol use, but definitely nitrogen plus methanol feed is there. So I think this question, if you know of Rajkiran.
No, sir, I'm not heard about the actually methanol and LPG both are the fuel, but we are not directly purged simultaneously in the furnace. So methanol plus nitrogens is the combination I heard or use in fast.
Yeah, Mr. Mandral, if you could.
Yeah, actually, one of the customer actually using the LPG plus methanol combinations. So I just wanted to check whether it is the right process or it is not the right process.
Actually, actually, it may not be a right process. Also, about the safety, also this process shouldn't be used because nitrogen will be, better process than LPG. It will be a risky thing to use LPG plus methanol. And I'm hearing for the first time somebody using this. In my around 30 years of experience.
Okay.
Maybe, sir, methanol nitrogen can be used for atmosphere and LPG can be used for enrichment.
Yeah, it is just like this one. Yes, you're right. Methanol plus nitrogen and LPG.
LPG could be, very little, only for maybe,
Okay.
Also, there is one fixture versus parts ideal loading ratio and fixtures material. Say around 66 to 70% of the part. That has to be the ideal thing, and say 34% could be 30 to 34% could be fixture. That is the thumb rule, but you can still go down and down. Like what we have seen in many furnaces, there are some people they achieve up to 30% of fixture weight and the part loading. But of course, the fixture should be very strong enough, and to take those load. But that is one of the thumb rule is around 66%.
Okay. Thank you.
Can you explain about ceramic coating? Who's Mr. BRP? Can somebody identify himself? Mr. BRP? Are you there, Mr. BRP? Okay.
Sir, can I explain?
Yeah. Good.
Okay. Ceramic coating is nothing but the ceramic particles is added in the refractory powder. that ceramic particle is non-conductive material, so that cannot be transfer your heat from inner surface to outer surface. And also, if you apply in the outer surface, the outer air cannot take the heat from the furnace walls. Also, in refractory powder, that because the refractory powder, your emissivity of the refractory bricks increased from 0.3 to 0.8. Because of that, your radiation heat loss reduces, and that radiation again pass inside the furnace and your temperature maintained uniformly. Also, another benefit is that your carbon is not deposited in the refractory bricks, that is porous, so that that carbon, in case of deposit inside the refractory bricks, that can be dead, and that will create the soot. Because of the coating, that carbon will not deposited in the refractory bricks, that will be exhausted into atmosphere, so that the positive atmosphere or a healthy atmosphere has been maintained throughout the furnace, and that will be impact on your final product quality.
There is one Mr. Jayesh Mukhadam. He is our member also, and actually a founder member of ASM. So we are, he is a commercial heat treatment plant. He has a commercial treatment for hardening and normalizing. And he's asking about any person or any agency help in furnace efficiency calculations and suggest coating for refractory.
Yes, two types of two agencies are available that will suggest you the heat loss calculation as well as the thermoceramic coating application. So please, I will share you later after this presentation the details of that suppliers.
That will be great.
The last question, which is main factors to enhance productivity, particularly the cycle time per se. So any factors to enhance the productivity, particularly cycle time reduction. That's what he's looking at.
I already explained, sir. Eliminate the NVA, that non-volatile activity in the process, as well as they use the boost cycle. Use the maximum temperature for oxidation nearby 900 to 925 degrees Celsius. That case, you can reduce the cycle time and use the 1 to 1.1% carbon potential. That time your carbon deposition rate is very high, and because of that, your cycle times can be reduced.
Okay, sir. Thank you very much. Yeah, thanks.
You can use the Harris equation for calculation of the any heat treatment cycle for that. So can you easily calculate the cycle for any component?
Okay. Thank you, sir. I'll get in touch with you if I need any more.
That is Harris equation.
Deep, no communication. Sandeep, are you there or you lost the connection? Sandeep? I think he has lost the connection. Vivek? Vivek? Am I audible?
Okay. Hello.
Yes.
Vivek, you can wrap up.
Yes, speaking.
I think Sandeep lost the connection. You can wrap up.
हाँ
Sandeep is not there, I think.
संदीप निकल गए हैं, आ जाएंगे अभी.
No, he must have lost the connection.
हाँ उनका वो एक बार पहले भी हुआ था, अभी दोबारा आ जाएंगे वो।
तो अभी क्वेश्चन आंसर तो खत्म हो गए ना, तो you can wrap up.
Okay. Rajkiran, everything has been finished, is it?
Yes, sir. Finish.
In the chat, no question is left which has not been answered. Hello. So good evening, everybody. Thank you very much for the meeting today. Today we had a lot of technical problems during the meeting and we are very sorry for it. We'll see that how we can improve that further. Thank you very much for attending. I'm ending the meeting now. Thank you.
Thank you very much, sir. Thank you very much.
Thank
Thanks a lot.
you, Rajkiran.
Thank you, everyone.
Thank you, Sudhakar ji. Namaskar.
Hari Om, Hari Om.
Hari Om.